Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on group, lecture number 58, in which I will discuss about automorphism. Let G with binary operation is a group and G prime with another binary operation is another group. Phi is said to be an isomorphism defined on G into G prime if phi is bijective. Number 2, phi is homomorphism. Then phi is an isomorphism. If phi is an isomorphism defined on G into G itself with binary operation O, then this isomorphism phi is called automorphism. Now we define automorphism. An isomorphism of a group G onto itself is said to be an automorphism. Now we give some examples. Example 1. The identity mapping on a group G is an automorphism, that is IG defined on G onto G defined by IGX equal to X is automorphism. Now we prove this. Let IG be the identity mapping defined on G into G as follow. IG is defined on G into G defined by IGX equal to X for all X belongs to G. Let X, Y belong to G and IGX equal to IGY implies that X equal to Y. Therefore, IG mapping is 1-1 mapping. This is number 1. For any X belongs to G, this is codomain. Here this is G, this is domain group G, and this G is codomain. For any X belongs to G, that is codomain, we get X belongs to G domain. We may get X belongs to G, this is domain, such that IGX equal to X. Therefore, IG is onto. This is number 2. From 1 and 2, we get IG is 1 1 onto mapping. That is, IG is bijective. This is number 3. Now, let X, Y belong to G. This is domain. Then IGXY equal to XY. Since IGX equal to X, therefore IGXY equal to XY. This X equal to IGX and this Y equal to IGY. This is number 4. Therefore, IG is homomorphism. This is number 5. From 3 and 5, we get IG defined on G into G is isomorphism. Therefore, IG is automorphism. That is, the identity mapping IG is automorphism. Proved. Now we give the next example, example 2. Let G be an abelian group and mapping phi defined on G into G defined by phi A equal to A inverse, A belong to G. Then phi is an automorphism. Now we prove this. Given that G be an abelian group and phi is a mapping defined on G into G such that phi A equal to A inverse, A belongs to G. Let B belongs to G implies that phi B equal to B inverse. A B belong to G implies that A operation B belong to G, implies that phi A operation B equal to A operation B inverse. Let this is number 1, this is number 2 and this is number 3. From 3, phi A operation B equal to B inverse operation A inverse. B inverse equal to phi B. operation phi A equal to phi A operation phi B, because phi A phi B belong to G and G is abelian. This is number 4. Therefore, from 4, phi is homomorphism. This is number 5. Now, let phi A equal to phi B implies that phi A equal to A inverse, phi B equal to B inverse, implies that A inverse whole inverse equal to B inverse whole inverse, implies that A equal to B. This is number 5A. Therefore, from 5A, phi is 1 1 mapping. For any element A belongs to G, we get A inverse belongs to G. Since G is a group, here this G is domain and this G is codomain. Here A belongs to G, this is G is codomain, and A inverse belongs to G, this is domain. We get that A inverse is the pre-image of A. We get phi A inverse equal to A inverse whole inverse. This is A. Therefore, phi is onto mapping. This is number 6. This is number 7. From 6 and 7, phi is 1 1 onto mapping. That is, phi is bijective. This is number 8. From 5 and 8, from 5 and 8, we get phi defined on G into G is an isomorphism. Since domain and codomain be same, therefore phi G to G is an automorphism. Proved. Now we give example 3. Let G is a group of complex numbers with binary operation addition, and phi be a mapping defined on group G into G defined by phi Z equal to Z bar. Z bar means conjugate of Z. Z belongs to C, means Z is a complex number. Then phi is an automorphism. Given that G is a group of complex number with binary operation addition, where C be the set of complex numbers, phi be a mapping defined on G into G such that phi Z equal to Z bar. Let this is number 1. Now we have to show that phi is an automorphism. Let Z1, Z2 belong to G. G means set of complex numbers. Implies that Z1 plus Z2 belong to G, means Z1 plus Z2 is also a complex number. Now phi Z1 equal to Z1 bar, phi Z2 equal to Z2 bar. This is number 2. This is number 3. And phi Z1 plus Z2 equal to Z1 plus Z2 bar. This is equal to Z1 bar plus Z2 bar. And Z1 bar means phi Z1 plus phi Z2. This is number 4. From 4, we get phi is homomorphism. This is number 5. Now let Z1, Z2 belong to G. G be the set of complex number, and phi Z1 equal to phi Z2 implies that Z1 bar equal to Z2 bar. This phi Z1 equal to Z1 bar, phi Z equal to Z2 bar implies that Z1 bar whole bar equal to Z2 bar whole bar implies that Z1 bar whole bar means Z1 equal to, this is Z2. This is number 6. Therefore, phi is 1-1 mapping. Let this is G, means set of complex numbers, C with binary operation addition, and this is also G, and phi is defined on G into G. Let xi belongs to G, here codomain. There exist Xi bar belongs to G, domain here. Xi bar. This is also a complex number. Such that phi xi bar equal to xi bar whole bar equal to xi. This is number 7 and this is number 8. Therefore, from 8 we get phi is onto mapping. This is number 9. From 7 and 9, phi is 1 1 onto mapping. That is, phi is bijective. This is number 10. From 5, phi is homomorphism, and from 10, phi is bijective. Therefore, from 5 and 10, we get phi defined on G into G is an isomorphism. Since here domain and codomain be same, therefore implies that phi is an automorphism. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and to subscribe my YouTube channel. Thank you.